Now for a concave mirror, if you have an object here, the situation will be more complicated, but the principle will still be the same. Let's still try to use the ray approach. So we use the P ray and F ray and the C ray to draw the image. Now, if you put the object which is behind the C point, now let's still try to draw the light emitted from the top of the object. You will emit a P ray, and P ray will be reflected and passing through the focal point. And now you don't have to draw a dashed line because they are all intersect by the real image now. So just a reminder that in our previous discussion, the image form is actually intersect by the virtual line. So the image form here is virtual. But the image form in the concave mirror, the image will be real because they are formed by the intersection of the real light. Now let's continue. So F ray will passing through the focal point first, and after being reflected, they will be parallel. So now you already have the 2 points and connect to and intercept to the same point. So now, without using the C ray, you can actually get the image. So you can see that the image is between the C point and the focal point. And the image is real, but it is inverted, and the size of image is smaller than the object. However, if you move the object closer, now it is between the C point and the focal point. Let's try to follow the same procedure. So P ray produced from the top of the object will be reflected passing through the focal point, and F ray will passing through the focal point directly after being reflected. It becomes parallel again. They intercept at this point, and now the image form actually is still in front of the mirror, but now you can see the size of image is bigger than the size of the object. But still, the similar property will be shared among these two is the image is always inverted, and also the size is not directly, it is not always smaller or bigger. It depends on the position of the object. But you may ask that, does it mean that all the image formed by the concave mirror is real? The answer is no. Now, if you move the object even closer, which is smaller than the focal length. So now let's draw the line first, the P ray. So P ray will be parallel to the axis first, and after being reflected, they're passing through the focal length. And now the F ray, they will be reflected and parallel. And you will find out the real F ray and P ray doesn't intercept here. Instead, the interception will happen if you draw the dashed line backward. So in that case, you will need also the C ray to give you help. So now you will find out the image form for concave mirror could be a virtual one and upright. And you can see now the image form is bigger than the original object. So now people will start to confuse themselves. So I introduce you the 3 different kind of scenario for convex, and now 3 different kind of case for the concave. And I show you that depending on where the object is put, the image form will be different. So here I will give you a summary about what we have discussed so far. For the convex mirror, it doesn't matter where you put your object. Then the image will always be upright and virtual. So now you can find out the pattern now. If it is upright, you can always say it is a virtual one. And the image size is always reduced. So for the convex, it is much easier. But for the concave mirror, it becomes more complicated. So if it is beyond the C point, which is the one I just showed you, the first case, the image form will be inverted, but the size will be smaller, but the image is real. And the special case you can give a try is if you put the image on the C point, the image will be inverted, but the size will be exactly the same as original size. And the image will be inverted and real. So you can see that every time when it is inverted, the image is real. And now, this is the second case I show you. If it is between the F and C point, the image is still real. It is inverted, but now it will be bigger than the original size of the object. And now if you put it just beyond the focal point, which is the thing I did not show you, if you just put it just beyond the focal point, it will be inverted and real, but now you can make the size approaching infinity. So you can now even see the whole image of that now. So you can see that the pattern here is that when you try to move the distance of the object closer and closer and approaching to the focal point, the size will become bigger and bigger, but all the image is real and inverted. But now, just after you pass through the focal point, and it is inside the focal point, the image will immediately become upright, and which is virtual. And now, the further away from the focal point, when they are approaching closer and closer to the mirror, the image now will become smaller and smaller. But still, the size is still bigger than the original size of the object. So this is why people will get a little bit confused. But I would suggest is that the best way, before you remember that is, use the ray tracing approach I should show you in the previous slide. Try to find out, did you know how to find out how the image was formed in the concave and the convex scenario? So now this is a summary about what we have learned so far about the image form in different kind of mirrors. For plane mirrors, the distance between the image to the mirror and the object to the mirror are always the same. And not a surprise to you, the image was formed by the virtual line. So which is the image is upright and virtual, but the size is exactly the same as your size. But for the concave one, or for the convex one, the size you form is always smaller than the original one. And for the concave, then it depends on where you put it. So concave, convex, and plane mirror. So the image form really depends on the position and on the curvature of the mirror. Now let's try to have our first quiz today. If you put an object 0.5 away from a concave mirror, and the focal length of the concave mirror is 1 meter, and what will be the answer? So just to remind you that a concave one, and you put that here, smaller than the focal length. So now with that hint, the answer is trivial. So the image form will be virtual, and it will be bigger than the object. So which means we are better studying about this case. You put it just inside, so no matter where it is, the image is always virtual and bigger than original size of that. So now let's continue our discussion. So the mirror equations. So I have introduced you the size of the object, which is h0, and the size of the image, which is hi. And the distance from h0 to the mirror is d0, and the distance from the image to the mirror is di. And we find out actually there are the connections between the d0, di, and focal length, and that is the mirror equations. And now I'm going to derive that for you. So now we have to use the geometric property of the triangle. So now this is an arbitrary light from the top of the image, so they will be reflected. And now they hit at the center of the curvature. So now the normal line is actually the axis. So it is not a surprise to you, this is a reflected light and they both have the same angle. And now the image, let's assume it is formed here. So we will say that now if you compare this triangle, this is the first one, and this is the second triangle, we will say these two angles are similar. When we say similar, we mean the ratio of the size will be the same. So now for the first triangle, the h0 divided by the d0, this ratio will be the same as the ratio if you're using the second triangle. So now, this 1 is no longer positive, it is negative. So it is negative H0 divided by the D0. So these two ratios should be the same because the two triangle is the same. So people will ask why it is negative. It is because H0 is negative. So in order to make this value positive, you have to put a negative sign here. Huh? So this is the first connections. However, you cannot even see the connection to the focal length. So now let's try to use the second relation here. So it is the same process, but now what you are going to connect is the top of the object to the center of the curvature and to the top of the image. So this is a so-called C-ray. Yeah? So now you connect these 3 points together. And once again, you will find out these two triangles are similar because the angles are the same. So therefore, the ratio of the side H0 divided by the D0 minus R, which is the ratio of these two. So you may ask why this is a D0 minus R. Yeah? It is because that from the center to the curvature, here it is the radius of the curvature, and now the distance from the object to the center is a D0. So this part will be D0 minus R. So now the ratio for the first triangle will be the same as the ratio for the second triangle. So it should be H0, but it is negative H0 now, divided by the R minus DI. So now these two ratios should be the same again. So now, based on these two results, you can rewrite this equation in terms of the D0 divided by the DI. And also you can rewrite this term in terms of D0 divided by the DI. So in that case, so let me correct what I just said. You can rewrite this equation in terms of H0 divided by the HI. And also this term in terms of H0 divided by HI. So now these two H0 divided by HI should be the same. So now based on that, from the first H0 divided by HI, you got this relation, and the second H0 divided by HI, you get this relation. And from this one, you will get the ratio 1, which is this. I will say, okay, it seems it's getting more complicated now. But you will find out if you substitute that the relation, the focal length is just 1/2 of the radius into this formula. If you substitute R by the 2F, then you will get the result to this equation is that 1 over D0 plus 1 over DI is equivalent to 1 over F. So this is the so-called mirror equations. So just remind you what do we mean by D0. D0 is the distance from the mirror to the object, and DI is the distance from the mirror to the image, and F is the focal length. And now you can connect these three variables together through the mirror equations, and this is true no matter it is for the concave or convex mirror.